This presentation is about task 4.1, data modeling and semantic alignment, where we used pilot number 2 to showcase our developments. In the context of a pilot number 2, one of the goals is to provide real-time assessment and monitoring for two standard risk metrics, value at risk and expected shortfall. In this scenario, we want to use semantic technologies to align data from different brokers so that we can detach the value at risk calculation process from the specific broker data formats and semantics. The developed solution is aimed to show how semantic and knowledge graph technologies can help financial organizations to semantically harmonize their data by aligning them to common semantics such as FIBO, as well as to provide easy access to any external applications. The first step is the analysis of the domain and the design of highly specialized graph models for the specific application. The graph models need to be, from one side, aligned to reference ontologies and from the other side to be linked to the specific data from the pilot. To do that, mappings between the raw data and the knowledge graph models need to be specified. This latest part of the proposed methodology consists of 4 steps: injection of the raw data, applying the mappings according to the created models, generating the correspondent linked knowledge graphs, and finally, the provision of the harmonized data. The video summarizes the overall process by using GraphDB software tool. At first, the raw data is injected by loading local or remote files, or through JDBC connectors to SQL databases like LinuxScale or Postgres. The imported data is structured in tables with the model attributes defined in the data modeling process. Users are now able to use a set of utilities for combining the imported data and creating the alignment with the INFINITECH core ontology. The mapping is done by transposing the pre-established relationships between the raw data models and graph data models. This is done by associating each term to its semantically equivalent. These mappings can be stored and used against other similar datasets, while more complex mappings can be also defined more proficiently through SPARQL query language. Once the mappings are defined, the users are now able to generate the linked knowledge graphs by executing either the specific SPARQL queries or, in alternative, the JSON mappings. In both cases, the knowledge graph can be generated and collected in one of the several RDF formats, such as Turtle or JSON-LD. Moreover, it is then possible to either store the generated graphs inside GraphDB or any other graph database by forwarding the data using any application developed for this purpose. Finally, since the knowledge graphs are created and stored, they can now be accessed by means of executing SPARQL queries against the Triple Store, making use of the available REST APIs. The REST APIs supply a way for outsider applications to reach out the generated knowledge graphs and extract the desired sets of linked data to be used on the analytics, as well as to insert or modify the existing data or even to manage the graph database. In the end, when several datasets from different sources and different formats are aligned and transformed with the same graph model by following this methodology, they are now available for querying and possibly extracted in a standardized format. So, INFINITECH pilots are now able to use this methodology for generating knowledge graphs data and use it inside their analytics or algorithms. Now is the time for pilots to take the lead and start exploiting semantic technologies.